Hi guys, Miss Zimmer here. We're in a new chapter. Congratulations, you got through with chapter 9. Now we're moving on. We've done our first chapter of remote learning. And now you're looking at 10.5. You're probably wondering, where did 10.1 through 10.4 go? Well, actually, we're going to be focusing on circles. So we're taking one section from 10.5 and then we're jumping over to chapter 12. Eventually, we'll go back and pick up some sections from chapter 10 and chapter 11. So that's intentional. You're not reading it incorrectly. So let's start in 10.5, which starts with defining circles. First, a circle is a set or collection of points. There are points on this circle. All of these points are the same distance from the center point. So what makes the circle unique is the center point and the radius. So if we're going to name a circle, we're going to name it by its center point. The way that we name it, we either say the word circle, capital P for the center, or we make an actual circle or an O with a dot in the middle. If you don't include the dot, then it just looks like an O or 0. P. So circle P or circle P. Obviously, if you want to name the center, you just put P because it's already a point, no dot necessary. So if we're naming the circle, circle P or center P. If this letter changes, so does that letter. We cannot use A or B because they're not in the center. Now, if we're naming the diameter goes across the circle through the center. The diameter can be named AB, and yes, it can be turned around, BA. We would not use a line, we'd use a line segment to name it because it have to have endpoints on the circle, and it must end, it cannot be continuous. A radius is half of a diameter. So AP is a radius, and PB, also a radius. Can we put PA? Could we put PB? Yes, those would be correct because we know segments are reversible. So technically, I didn't even have to write this twice. Writing it once, perfectly fine because segments are reversible. Now, central angle. I'm going to add another point. I'll put a point over here, C. A central angle is an angle with its vertex at the center. That's why it's central. So an example of a central angle, BPC. Another central angle, CPA. Another central angle, APB. You're like, but that opens up all the way. Well, yes, it does. And it makes a very large angle here, 180-degree angle, but still an angle. BPA or APB. So could we have an angle like APC? We could. So we could have angles that are greater than 180 degrees. Previously, we did not, but it is certainly possible. Generally, we stick to 180 degrees or less for most of the problems that we're going to solve here. Now, the next term that you'll see here, congruent circles, kind of shoved in there. If two circles, for example, if we do two circles, and we said both of these have a radius of 3 inches. If they both have the same radius, they're congruent circles. So they just have to have the same size, and the size would be determined by their radius. Now, if somebody says, well, what if they have the same diameter? Well, if they have the same diameter, the radius is half of that. So of course they have the same radius too. So that's fine. Same radius or same diameter. But we usually just define it with 1, the radius. Okay. Now, moving on, we're going to talk about arcs. I'm going to start with a new picture. We're going to talk about a minor, major arc, and a semicircle. So let's go ahead and use the same drawing. I'm actually using the notes that I attached to this materials section in Schoology, so you can certainly print them up, follow along, and fill it in if you have a printer at home. If not, you can simply take notes as you go along, using these sort of as a guide so that you don't have to fill in every single thing as I'm saying it. So this particular one is circle R. And let's go ahead and call this P and S. I think I had 2 R's, but let's make sure that this one is a P. All right. So minor arc. If it's minor, the arc is less than 180 degrees. So a minor arc could be from, for example, T to P. In fact, let's make it look even more obvious that it's minor, less than 180. Let's make it T to P. All right. Yeah, we'll leave that. Or P to S, minor arc. Or T to S. Now, contrast to that, a major arc. A major arc, and I should use the term arc, ACR. A major arc is greater than 180 degrees. So if I started at T, in order to do a major arc, I'm going to use 3 letters. Notice I only use 2 here because a minor arc's only going to use 2. That lets you know it's small or smaller than 180. Here, if we start at T, P, S, we see 3 letters. We know that it's at least 3, 180 or greater. And in this case, a lot bigger because it almost goes around the circle. If we started with P, S to T, that also is a major arc. If we started at S, S, T to P. Now, how you can tell these are all different arcs? Well, they all end at different places or have a different middle letter. So they would all be different arcs. And we say SPT, would that would actually be the same arc, just going in reverse. So it would be the same thing. So a major arc greater than 180. Well, let me put a Q in here now. How we would know if we have a semicircle is we need a half of a circle, exactly 180 degrees. So we have one on this side, we have one on this side. But if we just say TQ, which one? This one or this one? It's not clear. So we have 2 semicircles, TPQ or TSQ. Those are both semicircles, half of a circle. All right, so that takes care of minor, major, and semicircle. Just remember, minor arcs, always 2 letters. And if we were going to go from P to T, you would always go the shortest distance possible, not the long way around, so that you get that minor arc, not the major one. If it's major, 3 letters. Okay, moving on. I think we've named a few of those. Let's talk about arc measures. We know there are 360 degrees in a circle. And we've already said that arcs can be less than 180, minor, greater than 180, major, or exactly 180 degrees. So we've said that arcs can have degrees, just like angles. And of course, since a circle has 360 degrees, that makes sense. So now let's jump into arc measure relative to our central angle. So if we had this angle, 50 degrees, a little bit about notation. If this angle is 50 degrees, and we say measure of angle S equals 50, then this arc, we call that our intercepted arc. Just like if a football player throws a pass and somebody catches it, we're throwing these angles or these rays out to those points. So that arc is intercepted or caught in that angle. So we can say little m, just like angle, the measure of arc RT is also 50 degrees. So that means if we're having a 50-degree pizza slice, we're also getting 50 degrees out of 360 for the crust. Okay. We also can say that the other arc, RQT, is 360 degrees minus that 50. So this angle would be 310. Since the angle would be 310, the arc would also be 310 degrees on the other side, the one that's not in the original. All right. Adjacent arcs. Adjacent arcs are arcs that are side by side. So let's say I knew that this arc from Q to R was about 70 degrees. If that arc was 70 degrees, we could actually find QRT, measure of arc QRT, by adding together QR and the measure of RT. Since QR here is 70 degrees and the measure of RT here is 50 degrees, we can say the measure of arc QRT is equal to 120 degrees, 120. It's probably more than that based on my picture, but I just threw out a number there. So it's probably a lot larger. Probably should have made this angle maybe 100, okay? So that it would make a little bit more sense with the picture. But you can add arcs together is the point. Okay. Probably to make a little bit more sense, I could move Q up a little bit. And then it would make a little bit more sense there. Okay, sure. All right, let's do a problem very similar to what you might see in the homework. These can be either very simple problems or they can get really complicated if they throw in a lot of lines in the picture. It can look complicated. So a basic question might say, hey, I've got this angle and it's 30 degrees. What is the measure of arc BC? Or converse to that, say, hey, I've got this angle, it's 100 degrees. Let's make that even 160. Let's say 160 degrees. What is the measure of angle T? Well, since the angle and the arc are the same, the question is, well, the arc is 30 if the angle is 30. The angle is 160 if the arc is 160. So that's pretty easy to solve. So let's move on to something a little bit more complicated. This would be example 2 in the notes if you're following along. So we have circle O. This is A, C. That is a diameter because it is going through the center. Both points are on the circle. We also have D and B. And this angle is 32 degrees, and this angle arc is 58. Okay, first question. What is the measure of arc BC? Well, if the angle is 32, the arc is 32. Second question, what is the measure of arc BD? Well, BD, the arc is given, 58. Oh, excuse me. No, the arc is not given. CD is given. BD is 32, this arc, plus that arc. Excuse me, wait, to get it all the way from B to D, we would have to add those two together. So now we have 90 degrees. Okay, so we can add those arcs just like before. All right, let's look for ABC. Well, as I said before, this line, this segment here, that's a diameter. I just drew the line to kind of cut that circle in half. So you can see that this half, or measure of ABC, sorry, that's supposed to be a B, ABC, A to B to C, that's this half of the circle, so 180 degrees. And then the last one, AB. AB, well, 180 minus 32. 180 minus 32, 150, 148. All right, I'm going to just take a quick pause. I'm going to check on my power, and then I will continue with the next one. Just pause for a second. All right, I'm just doing a quick plug-in, and then I can continue this lesson. My apologies, 100% power, and I must have really run it down really fast. Excuse me. Okay, and now we're back in business. All right. So let's continue with the next example. So circumference and pi and diameter. Let's talk about that for just a second. Most of you think of pi as 3.14, an approximation. Well, if you hit pi on your calculator, you actually get a lot more than that. You get 3.14, 15, and so forth. It just keeps going and going and going. So where does it come from? Well, pi is actually your circumference divided by diameter. Circumference divided by diameter. And what happens is this. If you take that diameter and then you stretch it around the circle, it goes once, starting here, once, twice, 3 times, but it comes up just a little bit short. And that is where the 1, 4, 1, 5, and so forth comes in. It doesn't quite, 3 times doesn't quite finish the circle. So hence pi. So if you take a whole bunch of circular objects at home and you take your bendy ruler, if you happen to have it, and you measure the circumference and then you find your diameter, make sure you're really careful getting your diameter, and you divide it, you're going to come up with probably really close to, not every single one because there's measuring error, but you'll come up with a really close number to 3.1415. Now, if you don't have your TI calculator that we commonly use in class, make sure that you use 3.1415 unless my math lab frequently says use 3.14. If they tell you to do that, that's fine. If they don't tell you to do that, you should use the pi key on your calculator or 3.1415 to get a much more accurate answer. So, why am I talking about circumference? Because we already did circumference and area in earlier sections at the beginning of the year. Well, it's because we're going to need that. We're going to use circumference again, and we're going to talk about arc length in just a moment. So just a quick reminder, circumference is equal to 2 pi r, or circumference is equal to d pi. Sorry, that's still a C. I put a little curly Q. Remember that r is the radius, so d, standing for diameter, is 2 times the radius. They just don't put the 2 and the r together. So these are actually the same thing. One plugs in radius, one plugs in diameter. So if I give you a circle, and I said the radius is 3, then our exact circumference, not just approximate, our exact circumference would be 2 times pi times 3, or 6 pi. We're going to be using a lot of exact measures, so make sure you stop there, okay? If you use your calculator and approximate it, again, use the pi key or 3.1415, but don't approximate it unless they tell you to. Same thing here, diameter. Let's say they give you a different circle. That was a bad circle. And the circle, they say, hey, the diameter is 12. Well, all you have to do is plug in for d pi, plug in that 12 pi. You've got it. That is your diameter. So now that we did a refresher on that, let's do arc length. All right, arc length formula. Now, don't confuse arc length with degree measure. You're going to be using degree measure to help solve arc length. So I'll show you really specifically what each one is. So if we take this formula, we'll use the one that the textbook uses. They use a variety here, but the arc length, or AL, is equal to the degree measure over 360 times circumference. They also have a different formula in your textbook with arc length over divided by circumference is equal to m over 360 as well. Okay, because the degree of the arc over 360 would be the same as how long is that arc over the whole circle, which is the length all the way around. So either one of these works just fine. This is proportionate, as you can see. This is just another way of thinking of it as a fraction of the circle. So it may not be making sense yet, so let's dive into a problem and see how to use this. So let's do this problem. The problem would be example 4. A. They give you this picture. It's 16 inches. Sorry, the inches didn't come out very well. IN, period. That's supposed to be 16 there. Okay. And they ask you, what's the arc length of XY? Arc length of arc XY. They'll write out the word arc length, but I put A period, L period, so we don't have to constantly write that out. So please feel free. So this is O, Y, and, excuse me, 90 degrees, X. So now you've got the full picture. Well, if we're looking for that, we can use either formula. I'm going to go ahead and, let's go ahead and use this one. This one's really convenient in the book. So the arc length of xy over the circumference. Well, what do we say about circumference? Circumference is the diameter times pi. So 16 pi, that's our circumference. It's the measure of the arc. Well, the arc is right here, xy. It's 90 degrees here, so it's a 90-degree arc. And how many degrees are in the circle? 360. So if there's 90 out of 360 degrees, how long is it out of 16 pi? Well, this makes it look a little more complicated. So what we can do is just put in like an x value or something here for a moment. Let's say we're looking for x. Like, well, it still doesn't look right because there's a pi there. Well, think about this. This is x over 16 pi. And isn't this 1/4? Looks a little simpler, right? 4 times x is 4x. 16 pi times 1 is 16 pi. How do we get x, or our arc length, by itself? Divide by 4. So x, representing that arc length, is equal to 4 pi. And we want the exact answer. Now, if they tell you to plug it into 3.14, you can do that, or you can hit the pi key if they ask you to approximate, and then just follow a rounding procedure. Are they asking you for tenths, hundredths? It would probably be tenths if it was approximated, but they're going to ask you for a lot of exact. So this is the arc length of xy, 4 pi inches. Okay, 4 pi inches. Sorry, I think it fell off the screen a little bit. We're used to that in class. It's nice to have something the same. All right, so now that we have that one, let's do another arc length problem. One doesn't always get it done. So this is still an arc length problem. And in this case, we've got our circle, and we have a radius this time of 15 centimeters. We have 240 degrees, but that's out here. This is the 240 degrees. It's around the long way. We're asked to find, let's go ahead and still do xy. What is the arc length of xy? Well, it didn't give us the degree measure of xy, but we can certainly find the degree measure of xy. Remember, the measure is in degrees. The arc length is like inches, feet, meters. It's a length. How long is it? So 360, subtract 240, we get 120 degrees for the measure of xy. So now we know this one. So when we're looking for our arc length of xy out of our circumference, what's our circumference? Well, this time we have radius, so it's 2 pi r. So if our circumference is equal to 2 times pi times radius, our circumference is 2 times pi times 15. Well, what is that simplified? 30 pi. There's our circumference. And then we put degree measure of the arc over 360. Well, what's that degree measure? Well, we found out it was 120. Well, what fraction is this? 1/3. So our arc length, we'll go ahead and just put an x value in there for solving purposes. 30 pi. What happens when we cross multiply? Well, let me get the circumference out of the way. 3 times x, representing our arc length, is equal to 30 pi divided by 3. X is equal to 10 pi. So that means our arc length of xy is equal to 10 pi, exact. And if, again, they ask you to approximate it or to multiply by 3.14, you can do that. Just follow the rounding instructions from MyMathLab. Okay, so that's a little bit of arc length. One thing I can say about exact answers Sometimes they will end as a fraction. Don't let that bother you. It does happen. So if it happens and you go to divide, and let's say this number is a 2, or a 7, and you can't divide by a 7, then just leave it as a fraction. That is still an acceptable answer. That will happen sometimes. All right, let's end it here, and I hope that you will join into whichever Schoology conference is for your class. It may be at 2 o'clock for the geometry honors class, or 2:45, excuse me, for the geometry class that is my 8th period. So 2 o'clock and 2:45. Hope to see you there for any questions and answers you may have. Have a great day.